All right, so we're going to talk a little bit about thermochemistry. So a couple things. Oh, I can't get my pen to work. There we go. So thermo means heat. So thermochemistry is heat. It's simply heat lost or gained in a chemical reaction. So that's what we're going to talk about. So the changes in energy. So a couple things. We can say that energy is stored in chemical bonds. So if you remember that, lose it down here, that was called chemical potential energy, right? And the symbol for energy is going to be Q. Okay, so when you see Q, Q means energy. All right, so changes in the storage or release of chemical potential energy in the bonds. So that's the key there. They're in the bonds of a substance. So thermochemistry, the unit of thermochemistry is enthalpy, H, and when you see a delta H, remember this triangle here means change, right? So delta H is the change in chemical energy from reactants to products. Okay, so now we got that out of the way, let's move on. So there's two types of basic chemical reactions involving heat, one being exothermic, and this exo means out, and there's endothermic, and endo means in. So exothermic means releasing heat, and then endothermic would be absorbing heat. Okay, so two different things, endothermic and exothermic. So exothermic reactions we'll talk about first. So they are reactions that liberate, right? It's a fancy way of saying releases, right? Releases heat energy. So if we have reactants, yield products plus heat. So an exothermic reaction will release heat. Remember the laws of conservation. So mass is conserved, matter is conserved, and energy is conserved as well. So we can say here that reactants in joules is greater than products. Right? So reactants, the energy of the reactants is greater than the products, and it's solely for the reason that the products released heat. Okay, so that heat comes away from the energy. So delta H is going to be, or let me say it a different way. So you have a negative delta H, right? So the change in energy is negative because the products, and the way we get this is we say that joules of products minus the joules of reactants equals negative delta H, right? So products are less than reactants, so you're going to get negative. Right, so here's some conditions that sometimes cause. So formation of new bonds, right? Bonds are between electrons. Remember our kinetic molecular theory? If I put energy into something, eventually it becomes from a solid to a liquid and a liquid to a gas, right? Because the intermolecular attraction becomes less than the kinetic energy moving things around, right? But so to get things to stick together, I've got to take energy out to get it to stick together. So formation of new bonds, synthesis of more moles of products and reactants. Again, that has to do with formation of bronze. And then increasing order through a phase change. So let's look at our phase changes. We have solid, liquid, and gas. So exothermic would be heading this way. That would be exothermic. So the phase changes, we would have right here, we would have condensation. I've got to take energy out of a gas to get it turned into a liquid. And then right here would be freezing, or it's called solidification. Oh, I lost my color change. There we go. Right. So those would be your phase changes that are exothermic. Right. Right. So in an exothermic, right, heat is placed in the product. So if we were going to write a generic equation, I could say A plus B, I get AB plus heat. Okay, so again, I'm forming bonds and I'm releasing heat. So reactants contain more energy than products, right, like I said there. All right. Okay, so this is an exact, so this I'm running out of battery in my pen again. Okay, so this right here so combustion reaction. Remember, combustion reaction usually involves fire, right? That's a classic example of an exothermic reaction. So I've got propane, right, like you'd have in a camping stove, and oxygen, right? And I get carbon dioxide and water, and heat and light energy, right? That's a classic combustion. So the question is, where did this come from? This energy came from the reactants, right? So reactants, more energy, and this is less energy. Okay, so the Q of the reactants is greater than the Q of the product. That's another way to say it. It is greater than the Q of the products. Okay? All right. So another way to look at it, here's a reaction graph, right? So here I have reactants, and here I have products. Okay, so my reactants start at about 400 joules, or this is probably kilojoules. So joules, those are quantities of H, right? So we use joules or kilojoules for energy. So in my products are at 100 kilojoules. Right, so my delta H here equals negative 300 kilojoules. Okay? All right. Oops. I don't know why that's doing that. Okay, so let me come back to here. So my delta H is negative 300 kilojoules. We'll talk about, later I'm going to talk about calorimetry. We can see that Q equals negative delta H, right? So if we were going to say that, then we could also say that 300 kilojoules is is released. Okay, so there's a couple other things that are important in this equation. This right here is what they call E sub A, or activation energy. Right, so that's called E sub A. Let me clean that up a little bit. Or activation energy. So this is energy required to start an act. And these right here on the top would be our transition state or intermediaries, right? Energy required. So in most reactions, there is an activation energy or energy I have to put in, but that's not included in our calculations from reactants to products, okay? Right, so that's exothermic. Energy is released, products have less energy than the reactants. Endothermic reactions. So everything we just talked about for exothermic are just about opposite for endothermic. So, oops. So this should say endo. I just noticed it. So endothermic reactions are reactions that absorb heat energy, right? So we could say that Q is less than Q products. Right? And then delta H is going to be positive. Right? We're going to have a positive delta H because our products are going to have more energy. So usually we have it, absorption of energy used to break bonds, decreasing order in a phase change. So remember, if I again had my solid, liquid, and gas, right? Going this way would be my endothermic because I have to absorb energy to melt something and I have to absorb energy to make a liquid become a gas, right? So right here, from a liquid to a gas would be vaporization. And right here, from a solid to a liquid would be melting. So both of those phase changes would be endothermic because I have to absorb energy to get there. Okay. So in the endothermic reaction, heat is being placed in reaction. So I could have AB becomes A plus B. But here, I would have to put the heat because it would have to be absorbed. And we'll see that that explains that, right? So my products would have more energy than my reactants because they had to absorb it to get there. Okay. If I looked at this graph, here's a similar kind of graph. So I have my reactants here, and I have my products here, right? So you'll see that here now, from here to here, right, is my energy required to start the reaction, right? So my E sub A is 40 kilojoules. And my overall change, my delta H, is 100 kilojoules. Right? Together these are 140, it says there. All right? So my Q here is negative 100 kilojoules. Because remember I said that Q is negative H. So if H is positive, Q is negative. So what that means is I had to absorb 100 kilojoules of energy, right, to get to my products. Right? And you can simply look at, here's another example, right? If you looked at the first one, you knew this was exothermic, right? Because my products have less energy than my reactants. Here you would know this is endothermic because my products have more energy than my reactants. All right, another way to look at it is down here. Exothermic releases heat to the surroundings. Right? My endothermic absorbs heat. My H is negative here, and my H is positive there. So this is the temperature that's my environment temp. So in an endothermic reaction, my environment gets cooler because it gave energy to the reaction. In my exothermic, my environment gets warmer because my chemical system's releasing the heat. All right, hope that helps. And I'll look forward to another screencast, and I'll talk to you about calorimetry problems.